Thank you all. I'm very glad to share our latest work with you. Of the powerful recommendation approaches in modern recommender system, collaborative filtering makes prediction based on users' passive preference embedded in the user-item interaction of similar users. When it comes to mining users' preference or interest from the instances, matrix factorization plays an important role. However, in real recommendation processes, it may be not enough to consider only the user-item interaction behavior. It's also important to incorporate rich contextual data into the models to adapt the recommender system to the specific situation of the users. An intuition solution for introducing the contextual information, like user's gender, age, or item's price, to the graph-based CF models, is to pour the embedding of features into one vector, as shown in this figure. The consequence is that the model is not able to learn meaningful and explainable representation for user and items. This problem will be compounded by graph convolution. In fact, the graph defined by the user-item interactions is naturally a heterogeneous graph, implying that different types of nodes may fall in different feature space. However, the traditional graph convolution aggregates different types of features from different semantic space. As a result, the original semantics of node embeddings are destroyed. To address the problem of semantic damage when introducing contextual information into the collaborative filtering, we designed a novel context-aware graph collaborative recommendation framework. There are three components in CGCR: a feature space construction layer that initialized the embedding of users and items and mapped them onto the same subspace, a graph neural network layer that aggregates label information onto the target node, and the prediction layer using generalized matrix factorization. To preserve the semantics of features and offer the model explainability, it's necessary to construct a new feature space that contains all factors involved in recommendation. A natural choice is to expand the k-dimensional feature space of users with the r-dimensional feature space of items. Then, the final dimensional feature space is k plus r. This operation allows us to convert a heterogeneous graph to be homogeneous. As we can see, there are only single type of nodes in the same feature space. It enjoys the model with the flexibility to leverage the inherent complex relation in the data by graph neural networks techniques, while keeping each dimension relatively independent. It also allows each factor or contextual features to have its specific role in the representation learning, which is different from commonly used sum operation in feature fusion. The core to achieve collaborative filtering is to capture users' historical preference as well as high-order correlations between user and items. The aggregation and message passing involved in graph neural networks can easily resolve these two problems, on top of the converted homogeneous graph. Here are two aggregation functions, LGC and LGC+, using attention. To make the embeddings more traceable, we restrict each layer of graph convolution with constant dimension. Due to feature space expansion, the initial embeddings will contain many zeros in the extended dimensions, indicated by the blacks in this figure. Thus, the information is updated only on a part of the embedding. From this process, we can see that we didn't introduce any feature entanglement. The final representation of the users and items are obtained by taking the sum of the embeddings in each layer. We use the more generalized similarity function to estimate the matching degree. H is what we call the prediction layer. The above generalized similarity measure provides our model better interpretability. The feature dimensions are never entangled during representation learning and matching. Input feature dimensions can be directly associated with the component of H. We train the model on the whole data with the latest proposed efficient non-sampling matrix factorization. In addition, we use the efficient non-sampling framework to greatly reduce the training time. It can be found that the time complexity of the whole learning process is determined by the computation of loss shown in this equation. However, it should be noted that the feature space expansion in the first layer of our model compromises the computation efficiency. To evaluate the performance of the proposed method, we conduct extensive experiments on 5 datasets: Moviness, Zhihu, Pinterest, TikTok, and KKBox. We adapt 2 widely used evaluation protocols, HR at K and NDCG at K. We adopt the leave one out scheme of our ranking. That is, we treat all items the user doesn't interact with as negative samples and rank them. We compare our proposed models with a baseline method. We investigate the top K performance when K is 20, and the number of graph convolution layer is 3. For fair comparison, the embedding size is set as 22 for all approaches. The performance of our method on 5 datasets is shown in this table. And we can see that although the contextual information is introduced into NetGCN, the environmental result proves that our model is better than NetGCN. The comparison between our model and NetGCN reveals the positive impact of preserving the semantics of the embedding dimensions on recommendation performance, which is consistent with the previous conclusions of the importance of maintaining semantics. By using attention, LGC Plus has been further improved in most cases. The prediction layer is an important part of the CGCR model, which offers the model interpretability. It can be used to identify the importance of feature domains, which is indicated by the learned parameters h. We distinguish feature domains between users and item and no feature entanglement in every step. We provide the visualization of explainable results, and we can see that. First, the importance of feature domains is heterogeneously distributed. For example, in movements, model's recommendation depends mainly on the category of the film. Besides the ID features that embed the historical behavior of the users. Then, introducing attention into LGC has later effect on the importance of the feature domain. That is, historical record play a leading role in the recommendation. To see whether CGCR can benefit from multiple embedding propagation layers, we vary the model depth. It is shown on the 4 datasets that an increase of the convolutional layer will definitely increase the effectiveness of the model. And when the number of graph convolutional layer reaches 3, the effectiveness of the model will be weakened. Since the negative sample weight plays a key role in the non-sampling strategy, we study its impact on the recommendation performance under various metrics. The shape of the curve indicates that all models with non-sampling strategy are sensitive to negative sample weight. This suggests that in practical application, the first priority is to search an optimal weight for certain dataset. Note that the model have different optimal negative sample weight for different datasets. Their optimal values on the same dataset are almost the same. In fact, we could first search for the optimal negative sample weight using ENMF or ENSFM model, and then use it directly in LGC's hyperparameter setting. This approach can largely improve the learning efficiency. In this work, we take the problem of semantic separation when integrating contextual and user-item interaction information in collaborative filtering recommendation. We have proposed a simple but interpretable framework CGCR for context-aware top-key recommendation. CGCR not only connects graph neural networks and matrix factorization, but also preserves the semantic independencies of each feature domain. As a result, CGCR achieves 2 remarkable advantages. 1. Offers a solution to convert a heterogeneous graph to the homogeneous one. 2. Seamlessly incorporate contextual features to collaborative filtering with better explainability.